Zuppero and Thomas Dolan. Okay.
Thank you. All right. Let's see if we get this. Well, my name is Anthony. The only thing I want you to take away from this, from mine, is it's most curious. And that's it. What I'm bringing you is a model of our work in chemical physics. It had absolutely nothing to do with what we're doing here. Okay? The work was at UC Berkeley Chemistry under, with Gabor Somerjai. The others were at UC Santa Barbara Chemical Engineering, and let's get this to a, how do we work this? Yep. Next, how does it go? There. Okay, the work was, it was at UC Berkeley Chemistry where I was, did the work, and it was an obscure breakthrough. Obscure. It's curious because all the reaction categories I looked at from everything I could possibly read, they're all consistent with our model. That's not very good because every theorist says that. What makes this most curious is that when I apply what we did and I add in the muon nucleus research, because it's coupled, what I get is all the isotopes you're supposed to see, and you see them, and the isotopes you're not supposed to see, and you don't. And I model the difficulty with an effective mass, a number, and I get a reaction probability per enabling phonon. And so this is not a theory for you. It quantifies my chemical physics, the group, the people that we were in. So why am I here? Well, I made you stare at that picture a lot because our potential energy diagrams are the same. Now, my excuse for this is that for the slides being out of order, is I'm going to show you it's not that hard. But in fact, what we saw was, I saw carbon monoxide and oxygen on a catalyst surface, palladium. Palladium is friendly to semiconductors. It's totally different from this. And what we saw was impossible. Gabor Somerjai says, impossible, it can't. I saw an electron come out, way above thermal. Nienhuis over at UC Santa Barbara Chemical Engineering, he took a free radical, dropped it on a metal piece, you make a free radical medical bond, and a single electron came out with 3/4 volt. Cannot happen, it has to be thermal, okay? The defining publication, none of you, yeah, right, none of you, speaking Italian, parlo italiano, none of you could have known what I'm going to show you before November of 2011, because that's the first time this impossible thing was published, okay? The impossible thing is that the binding energy, and that's why, now we take a look here, and I want to see if I can, this, by the way, is a marvelous pointer, and yeah, nice. All right. We start off with reactants which are far apart, like almost a Rydberg state, okay? And there's two potentials. One doesn't care about the electron at all, and that's like a proton and a nucleon. They don't care about the electron at all. And the second is a bond, an electron which attracts them, okay? And so it starts out very far apart, and then the magic occurs. The energetic bond squeezes the electron, which is trapped in a bond between them, and because the reactant and its other reactant, I called it reactant and fuel, because those couple and connect, it ejects the electron. And the magic is that the entire binding energy can go to the electron, which means what's left doesn't have any energy to be in an excited state. It's born in the ground state. That should ring a bell with you, because that's what you've been seeing for 30 years almost, and that was the biggest conundrum. How the heck do you get born in a ground state? So here was our reactions. And then we noticed, when we were presenting this to Los Alamos to try and get rich, a deuteron and a proton, with the electron between them being a muon, what happened was that all the energy went to the muon and the helium came out in the ground state. So here's a nickel and a hydrogen. That should be familiar. Why, of course, you get a 6 MeV electron and copper. You see the copper, you should be alarmed already. Nobody has ever seen the 6 MeV electron. Well, of course, if you take a palladium and a deuterium, you should get a 13 MeV electron and you see the 107 silver. Liberian will show you that later. And the only thing I'm interested in is that the cesium-137, a radioactive output of a reactor, and a proton should give you 9 MeV, which I'm going to throw away. I don't care about it. All I care about is the product is an edible barium. It's not radioactive, okay? So now let's sketch the, you get that green thing out of the way. I'm gonna find the, well, there's the chemistry. Let's go backwards. How do we go backwards on this thing? There we go. All right. We're going to model this like an H2 plus ion, a proton, and an electron. Actually, it's a nickel with 28 protons, and so you got to do a little math, but we're going to do it simple because this is like freshman chemistry. Okay, and it's an H2 plus ion with an additional binding energy that doesn't care about the electron. Well, the strange part about H2 plus ion is there are no repulsive forces, no Coulomb repulsion. Well, it's not forever no Coulomb. It's stopped by momentum repulsion. We all learned that the electron repels protons. Remember? I was not taught that, but you're going to see what they teach freshman chemists. So what we're going to do today is we're going to figure out how small can we get that negative potential, that bond, so that we get just a ground state inside the compound nickel-hydrogen nucleus. Nickel-hydrogen together, if it was really in the ground state, it would be copper. So how would I get that electron to bring the nickel and the hydrogen together with just barely enough electron between them? Okay, that's the trick, and that is the trick. Now let's see. Yes, in the H2 plus ion, it's a sigma G, sigma Gerade bond. This is the wave function for the bonding wave function. Notice here's the nickel, here's the proton, and there's a bunch of electron density between it, okay? This is cold fusion. There is no electron between them. The density, if it comes down to here, there is none. And here is the only equation in the entire thing. This is the entire derivation. This is the Hamiltonian. This is all the energy. We use Heisenberg. Here's delta X, delta P greater H bar. The correct, precise, is the Robertson-Schrödinger equation. So it's sigma squared X, sigma squared P greater than H bar over 2. If you solve the Schrödinger equation, you can get rid of the greater than, make it equal, and fortunately, that thing is about 1, approximately 1. Now notice something else. P squared, sigma squared P, it's like the expected value of P squared in the center of mass coordinates. So P squared over 2m is an energy. And so it takes energy to squeeze an electron between anything, in this case, between two protons. And the only thing you should remember is that it's 1 over m sigma squared x. And Dolan says, make sure you tell them, sigma x is about x, approximately x. So it's not 1 over r, Coulomb repulsion, it's 1 over m r squared momentum repulsion. And that's the trick. So now if you just solve for what electron mass does that take, what you get is the only equation, and all we get is a threshold effective mass. So now you should be puzzled because I'm going to change the mass of the electron. That's puzzling. But we'll pass that one up. That's the 2-hour talk. This is the chemistry. This is the electron coming. He did it with a Schottky diode. This was the defining observation where there's the single electron, and this was in November of 2011. And here's me thinking I'm going to get rich. This is about 0.7 volts across a Schottky diode directly from that. And what we really want to know is, what if we put a proton and a nickel and another proton, because there are 2 protons with nickel make zinc. So now we got to put 2 of these between there. And what we have to do to make this work is we must listen to muon nucleus particle physics. They say use bare nuclei, ignore the electrons. And of course, if the student did that, you'd get an F in the course and he'd flunk immediately. However, that is what was observed. If you look at muon nucleus research, the heavy electron doesn't see the light ones. And Professor Dolan here, who's going to help me, his analogy is you have a golf ball on a table of ping pong balls. The regular electrons are ping pong balls. And the other thing, which is rather important, is that it was observed that the highest atomic number attracts the heavy electrons. What was observed was that when the muon was on a deuterium and it saw a neon dissolved in the 20 Kelvin soup they made, immediately that muon says, I see 10 protons. I'm leaving, and immediately quenched the reaction. No reactions. Okay? So these are the rules. Of course, it has to be exothermic, and the electrons in the fuel should be delocalized because they have to move like a H2 plus ion. So, well, that's real nice. What happens? Well, the normal thing you would expect, you get 2 hydrogens and a nickel, you get zinc 64, and 13.8 MeV, and so forth. And if you look at 4 deuterons and an Iwamura cesium, thank you, Yashiro Iwamura, doctor. You should get praseodymium. And of course, if you take 4 hydrogens and put it on 137 cesium, the radioactive one, it's already got the neutrons. All you got to do is supply the protons and you make praseodymium. Well, that's nice, but you have now a 13 point, if you're doing 2 hydrogens and a nickel, you got 13.8 MeV of smashing electrons inside the nucleus. What do you think is going to happen? Well, it fractures it. And now you are accessing other branches. Okay, so if you're a chemist, you recognize that that's an activation energy. And it's all in the fine print, by the way. This is real fine print. I'll read it for you. Oberacher in the year 2004 published that the activation barrier to spit out particles is something like 6.5 to 10 MeV. 6.5 to 10. I got enough. How about if I take deuteriums and the 105 palladium, which Biberian here is going to show us, so you make cadmium. Sometimes you see cadmium with 26.4 MeV. That's plenty enough to fracture it. So what are the branches you could have? Well, an interesting one is the 107 silver, plus a hot deuteron. Well, it's really going to be hard to see a hot deuteron when you started out with deuterons. You could also have, it could bust out, instead of a 107 silver, we'll bust out a 105 palladium and a helium-4. Well, look at that. You started with 105, you ended up with 105, and it looks like fusion. It's not. It's an attraction reaction. That's our name for the reaction. Well, you could also take another path. The palladium could keep a neutron, so 106 palladium, and you got helium-3. Now, the curious part about that is that that's what you see. You've seen the helium-3, the helium-4, and you haven't seen that electron yet. And so I'll show you that in a minute. So what happens? Well, the only thing I care about is neutralizing radioactivity, and I'll tell you right there. But if you take 4 deuterons and cesium-133, you get the reaction. But you get something else. And if you're a chemist, you understand autocatalytic reactions, which means you create something, and then you put that on the left. The second row is, well, you take this 141 PR with all that energy, and it busts up into 133 cesium plus 2 helium. Well, look at that. So while Iwamura was overjoyed that the praseodymium was appearing as the cesium-133 is disappearing, all I see was, hey, your catalyst is going away. Okay? So all I care about is transmuting cesium-137, and the reason is that there's 40 billion authorized to do this, and it's called cleanup, and my name is written on it, and I told my business partner, when I come here, I'm going to offer every one of them that I'll pay them. And he said, what? We're going to pay them? He wanted you guys to pay, somebody pay me. I said, yeah, how do you think you're going to get 300 highly skilled people with their full laboratory all of a sudden, right now? Here you are. So I'll share 40 billion with you. But this is all a fantasy because it only works if the electron is heavy enough. And that, of course, is where we came in. I first learned of electrons having not a mass of 1. In fact, this is a good example. No, an LED is a good example. Of course, you add light and you get the electron, but nothing happens because silicon is what's called an indirect semiconductor, so you must add crystal momentum. Now, this is a band structure diagram, energy, crystal momentum, and I know that there's several, at least many of you know what this is, because I asked, and a peculiar thing happens is that the effective mass, which you have to use in the Schrödinger equation, is 1 over the curvature. So the closer you get, if you just add a different amount of crystal momentum and a different amount of energy, closer you get to that thing, the heavier the electron, because 1 over 0 is a big number. And so the effective mass is 1 over the curvature. The Bohr radius is the curvature, and there's a big error over here. Take that 1 over away. The electron density, the density of electrons surrounding the nucleus that was just made by putting electrons up there, the density goes up like the cube of the effective mass. So what an alpha particle coming out of a nucleus is going to see is 3 or 4 orders of magnitude higher electron density, and every one of them is going to be an order of magnitude or 2 heavier. So immediately the helium, the alpha, is going to pick it up and neutralize, and you won't see it. Same thing with the other particles. And the electron, similar, sees 3 or 4 orders of magnitude higher electron density, so it thermalizes quickly. Now, here's where I get to laugh at those crazy cold fusion people. That only lasts 10 femtoseconds, and that's not long, okay? And the good part was that at UC Santa Barbara and UC Berkeley, we were all smart enough to catch the electron in less than 10 femtoseconds. But you guys sit around having coffee watching your experiment. Well, of course it's thermal. It's all heat. I got 4 minutes and 58 left. I want to show you. So how do you generate that heavy electron? Well, you have to knock the crystal momentum. You have to knock that thing halfway across the Brillouin zone, which means you have to have distortions which are less about like the crystal unit cell, just a few atoms. Well, if you're near a surface or wherever you enter, here a proton or whatever, you have adsorption, desorption, or injection. When you bang that thing in there, you're causing the crystal momentum wave, and the wave has a lifetime of about three picoseconds or more, and a dimension of order, it rings over a size that doesn't fade out for about nanometers, 1 to 15 nanometers. So what you end up with is a splatter of energy. You get a spectrum of energies that shoot into the energy side. You get a splatter of momentum shooting into the crystal momentum side, and it looks like a shotgun shooting the point. And that's real nice, because that's how you do it. And that tells you, of course, you got to be close to a surface. Well, something else interesting happens, and that's how you do it. Every time you add a crystal facet or a dislocation or another little something, you generate a pair of inflection points. And so now what happens is that you got this little nanocrystal. Well, it's all facets because it's never a sphere. And if you put in dislocations, of course, you're going to generate. So now instead of a shotgun shooting one bird, the shotgun shoots a whole flock. And so that explains why somebody here is going to tell you that defect density really counts. I heard it several times that you put defects in. Well, that tells you why that works. And this is why palladium is so good. It was, by the way, if it's hard to see, it was hard for me to see. The inflection points, you got to really look, because nobody gives a darn about inflection points. Look how close to the Fermi level they are. You almost don't have to add energy with palladium. Okay? Here's palladium hydride. The inflection point is somewhere in there. This is EV, about 1 EV, something like that. Something like that is a fourth of an EV. And you get that thermally, okay? This is why nickel is so good. You can't see it, and neither could I for a long time. But where those little arrows end up, near the Fermi level, here's the Fermi level, there's a bunch of inflection points. So that says this is rather interesting. So the only thing you got to do is, there's one thing left. How the heck are these things born in a ground state? Well, the total energy, which we had in that only equation that you have to look at, says that the momentum repulsion, 1 over mr squared, not 1 over mr, is so big. You get about 100 MeV of momentum repulsion keeping the electron out. You have a puny 23.6 MeV trying to bring it back down, 2 heliums, or 2 deuterons trying to make a helium. That's just not enough. But as that electron is rising effective mass, as it gets closer and closer to the inflection point, the ground state goes down and down, and just at the threshold, which I showed you how to do, the chemical level and the nuclear ground state end up being good for tunneling. So all you have to do is just calculate the gamma tunneling of not ions, but electrons. And what happens? Well, when the nucleus couples, the electron is no longer between them, and the electron has all the energy, and out comes the entire nuclear binding energy into an electron quasiparticle, and the nucleus is sitting there in a ground state.
You have to
Pardon? I have 7 seconds left. Holy cow. All right, well, the only thing you have to look for is the gamma tunneling probability, the threshold effective mass, and the fracture energy. And here is Biberian's silver 107, the helium, this. Bajitov reported the classic hydrogen reaction. Here's the cobalt, here's the copper, here's the iron, here's the zinc, and 2 helium. For every iron, you better see 2 helium or you're not adding up the protons and neutrons. How about the lithium, aluminum, hydrogen, nickel reaction? Well, Dr. Dolan here was yelling at me because I had every reaction showing you that every isotope reacts, but you have to react them with lithium 7 plus hydrogen. And that looks like 2 heliums, 4 deuterons. Okay, but if you do that, a particularly useful thing happens. And I noticed that, how do they get the silicon? How do they get the chlorine? Well, they had to react the aluminum. Aluminum plus hydrogen is silicon. The reason this is useful is that this path doesn't have higher probability for fracturing, so this one would generate more electron, and these would generate ions, particles. So now let's try a few more. It says the end, but I can't resist. First thing, every reaction that Dr. Iwamura saw is predicted. Then there was Urutskev. I'm running over, but I hope it's only, I'm only going to have a few of these. Urutskev had a foil, titanium foil, and heavy water. There was no hydrogen. And he said, I did it 200 times. Other people did it. We measured weighed the hydrogen. There's the hydrogen. What happens was I looked at this and said, wait a minute, there was no nickel in the system. There was no zinc. But here's the zinc, copper, nickel, iron. When you do the titanium plus oxygen, you get the nickel, the copper, iron, plus the hydrogen. So there was no hydrogen in the system, but this time I could see it because he started out with deuterium. And there's vanadium over there. Look at that. There's the vanadium. There's chrome over there. There's the chrome. This is the pattern that keeps appearing no matter what reaction I pick. That you guys, there was one that Biberian asked me at lunch. He says, back down there at Langmuir's time, almost a century ago, they dumped 10 kilovolts, 10 kiloamps into a little teeny-weeny tungsten wire, and the tungsten totally went away, and it was all helium. And I thought, okay, how does they do that? Well, the first thing, I thought, does tungsten work with hydrogen? So I go look, and sure enough, the effective masses are like 20, and the I forgot to show you something important. I'm time over. The effective mass, 64 for the titanium. For the, I'll just tell you, for the nickel reaction, it's about 35, okay? So this one's large, but for the tungsten reaction, it was only about 20. It's less than nickel, and sure enough, all the helium came out and nothing else. And I asked, gee, I wonder what the recoil energy is of the particles. It's about 300 kilovolts. Silicon Valley implants cesium with a 300 kilovolt implanter. So what they had was tungsten glass and helium. And I think that's it. Okay, I would like to have Dr. Dolan summarize. Okay. What? Done? Okay.